So my talk is Scalable Bayesian Nonparametric Dictionary Learning. And my talk title is also not totally representative of what I'll actually be talking about. So the scalable part will just be a bit at the end. Mostly I'll be focusing on Bayesian nonparametric dictionary learning. And so for the first part will be entirely review of using Bayesian nonparametrics for dictionary learning. And this is work that I was doing with Larry Karen when I was here as a PhD student. And so that's to set up and motivate the technique that we're using. Sorry. Then I'll very briefly talk about an application of that to compressed sensing MRI, because I think that's very relevant to this audience. And finally, I'll talk about new inference algorithm for doing Bayesian nonparametrics. And so that's basically two parts. One is a new EM-based algorithm, and also scaling that up to large data sets. And so this is actually, I think, the most interesting part, because unlike other dictionary learning algorithms, there's not really much theory about what you're going to learn using this Bayesian nonparametric approach to dictionary learning. There's a lot that you can say about the prior, but there's not much that you can say about what you're going to learn. And so what this algorithm does is it actually shows that this so-called BPFA algorithm is very close to KSVD. The way that you actually learn it is close. It involves an OMP-like step, and et cetera. And so this is, I have no theoretical results, but the motivation here is to maybe put it in the domain where some theory can be performed. So to review sparse dictionary learning and the beta process, I'm sorry if this is a little too simple for this audience, but we have for sparse coding of a signal, we have our signal X. We have some matrix W, I'll call that a dictionary. And then we want to sparsely code that with this vector where there are mostly zeros, and which are the white squares, and the black squares are the non-zeros, which pick out which columns in the dictionary are going to be used to model this signal. And so the sparse coding problem is actually taking this dictionary W and representing the signal X with this sparse coding vector alpha, where alpha has only a few non-zero values. And so now if we want to turn this into a dictionary learning problem, we have many signals in our data matrix. Each column is a signal. Again, we have a dictionary, and now we sparsely code each of these columns with its own vector alpha I. So xi, the ith column here, corresponds to the ith column there. And with dictionary learning now, we also assume that we don't know this dictionary as well. So the goal is to basically learn everything on the right side of this approximation, the dictionary, as well as the sparse coding of the signals in the dictionary, so the sparsity pattern, and then for the non-zero elements, what those values in that matrix are. So KSVD is, I think, the most famous way of doing this. So it consists of two steps. First, we have the sparse coding step, so that's A, the first picture I showed, where we want to, given a dictionary, given W, and holding that fixed, we want to sparsely code the signal, each signal in our data matrix with this vector alpha. So basically find the sparsity pattern, find where the non-zeros are in each column of that alpha matrix. And then given that sparsity pattern, we want to update the actual dictionary and the weights on the non-zero entries to better approximate the signals. So we go back and forth between those two steps, sparse coding each signal, finding which columns of W are going to be non-zero for each signal, and then holding that fixed, updating the dictionary and the weights on that dictionary in the non-zero locations to better approximate the signals. And so the objective that this is intended to optimize looks like this, where we want to maximize the squared error of our approximation of each signal with its sparse representation in the dictionary, subject to some sort of a penalty on the sparsity. So you could say that each column of this alpha matrix can only have T non-zero entries, or it can't have more than T non-zero entries. You could also say that just keep adding non-zeros until this approximation is within a certain range, and so on. I'm sorry? Oh, this is, yeah. So I'm going to become Bayesian later, where we want to maximize everything. So yeah, I'm thinking negative, and this is Gaussian and all that. This is minimization. Thank you. Yeah, it's very easy to maximize that, I guess. Okay, so again, I'm sorry if I'm going into too much detail and yet not getting into the math. But I wanted to talk more a little bit about what OMP is, because that's what we're trying to mimic with our Bayesian nonparametric approach. So the sparse coding step uses an algorithm called orthogonal matching pursuits, OMP for short. So this is step A of this two-step process. So there's an inner algorithm in step A. And so this algorithm for the first step is also a two-step process. So what we want to do is we want to first, in a greedy fashion, decide which elements, so which dimension in one of these sparse columns. We're focusing on a single sparse column here, so A. Which one are we going to make non-zero? And the way that we do that is we find the corresponding column in W and say which one is the most correlated with the current residual. Because if we could only add one more vector from W to approximate this signal, we want to pick the one that's going to be able to be stretched or flipped and stretched and get us as close to the signal as possible in Euclidean sense, because we have a Euclidean penalty. So then once we do that, we measure the correlation. It's a simple equation, and pick the column of W to make non-zero. We then update all of the active non-zero values in this sparse vector using least squares. So we pick out the submatrix of W that's turned on. We solve the weights for that submatrix using least squares, and then we take those weights and fill them into the sparse vector alpha I. And then keep doing that until we add 10 things, or T things, or until we get within a certain threshold of closeness to the signal we're trying to approximate or whatever. And then I also put this here because KSVD, then you use K rank 1 SVDs, but you could equivalently, if we want to define KSVD based on the objective function and the fact that we use OMP to learn it, then if that is enough to define what KSVD is, equivalently we could use alternating least squares, where we then just take the least squares, the sparse least squares learned matrix A, so the rightmost matrix, and then update the dictionary using a quick, easy, closed form least squares solution for that, and then go back and forth. So if you know probabilistic matrix factorization, it's the same type of deal, where you have two matrices, you do least squares on the left, least squares on the right, and then go back and forth. So I also mentioned that because in the algorithm we work on Bayesian nonparametric version. That's what we do. Okay, so now the question is, can we do some sort of a Bayesian take on this same exact problem? And so if we want to do that, we need to introduce prior distributions. And so the most natural and first place to look is for this sort of a sparsity-inducing mechanism is a spike slab prior. And so in this, what we have is that the signal is Gaussian. So now here I'm thinking maximization here, where we have the Gaussian. This is the negative squared error of our approximation. And then when we decide what we want to, for the I signal, whether we want the kth, dictionary element to be on or off, we say it's off with a certain probability, 1 minus pi k. So that's the kth dictionary element. It has a probability of being on. If it's on, we draw it from the actual weight from a Gaussian. If it's off, it's 0 and it's off with probability 1 minus pi k. And so that's what I just said here. So in this case, with this spike slab prior, every dictionary element, WK, the kth column of our dictionary, has an activation, gotta make sure not to fall off, has an activation probability pi k. And active means that we just pre-weight that dictionary element by a Gaussian random variable. And so that's a spike slab prior for this. That's the prior on the sparsity pattern and the weights. So now the natural question, and if you've heard my advisor Larry talk, this is what is the size of the dictionary? How do we learn the dictionary size? And also what are the weights? What are these things, these values that we're using? So my take on the podium is that the lip makes the slide off more of a slow process. So here's the actual prior of the model, and then I'll have the picture again to make it more clear. But what we have is, what we want is an infinite dimensional spike slab prior. So to do this, we start with a prior for a dictionary of size k. K is a non-negative integer. And then for each dictionary element, this prior is going to be a limiting process. So we're starting with a finite dictionary. We draw an activation probability for the kth dictionary element from this beta distribution, and this 1 over k here is very important. Then for each dictionary, we draw the column of the dictionary from just a Gaussian, spherical Gaussian. We draw all the weights from a spherical Gaussian. And now when we want to sparsely code the ith signal, we just do a coin flip and say if using the activation probability for the kth dictionary element, if it's 1, then it's active, and we use this. So we take this binary vector, put it on a column of a matrix, and then construct our approximation in this way. And what this matrix, this diagonal binary matrix, is doing is basically saying if I use the dictionary, I'm going to multiply the weight by 1. If I don't use the dictionary, I'll multiply the weight by 0, and it's, doesn't matter. And then that's the sparse coding. So in context of this picture, here's our data. Each column has a spherical Gaussian prior. Each row of this matrix has an activation probability from a beta distribution with a very special parameterization. Then to get the on-off of each row, I have an independent Bernoulli process where I just keep flipping a coin with a specific probability. And whenever it comes up a 1, I then draw a weight. So it'll come up a 1 if there's a black dot there, and then I draw a weight for it. That's the full prior. So now the question is, so are there any questions about that? Okay, now the question is, where does the Bayesian nonparametrics come from? Here's the theorem about that. So this is just basically a theorem about what's the limiting process. So if we do what I just described, and then we construct this random measure hk, where this is just a random variable. So if I take some set of my space that W is living in, so RD, and then I evaluate this measure on that set, I'm just summing up all the pi k's for which the WK is in that set. So that's a random variable. I want to look at the Laplace transform of this random variable and say, what happens when k now of this Laplace transform goes to infinity? What is the Laplace transform of the limiting process? And you get this. And so if you've studied Poisson processes, you're excited because you see this right here, which tells you everything you need to know. This is a Poisson process where, these two terms constitute the mean measure. So there's an underlying Poisson process of our model that we defined in the infinite limit, and that tells us that this is the process that what I'm calling BPFA, which is setting k to 500 or 1,000 or something big but not infinity. That's the process that this model that we're using is approximating. And so we can evaluate all of its properties based on that. I'm think I'm going very slow. So here's the picture of what that is. I'll skip that. And so here's what we can say about what this model is approximating. So this is the nice thing about Bayesian methods and Bayesian parametrics. We can say lots of things about the prior. You know, what types of models do we think we're going to see? What types of things are we going to see a priori? But we can't say anything then during inference about what we're actually going to learn. Like, do we recover the dictionary or not? But what we can say a priori is, for example, as k goes to infinity, how big is the dictionary? Like, how many dictionary elements are going to be used by n signals? And that is Poisson distributed with this parameter. These are just two non-negative eta and gamma parameters, hyperparameters. You have to set their non-negative numbers. And so you can say that it's Poisson distributed with, and in expectation, it grows kind of like gamma log n. So the number of dictionary elements grows like the log of the number of data points that we have. We can say how many dictionary elements will be used by any given observation. That's Poisson gamma. So gamma is a parameter. I think that each dictionary, each signal is going to use 10 dictionary elements. That tells me I should set gamma. If I want to use this model, I know I should set gamma to 10. But the upshot is that we can just set k to a large value, like k equals 500. And even though we're setting k, we don't have to justify how we're setting k. So that's nice. Because even though k is 500, when we do inference, we're going to not learn 500 dictionary elements. We'll learn 200, and the rest will be empty. So I thought I would be going much faster than this. So here's one very quick two-slide example of this to compress sensing MRI. So to refresh your memory, we start with a subsampled Fourier basis. So the Fourier basis vectors are the rows of f, and then we sample them in some way, subsample them in some way, and measure these Fourier coefficients y. That's our measurement, which is just those Fourier coefficients of our signal x. And we want to optimize something like this, where we want to minimize the squared error of our reconstructed x, the Fourier coefficients of our reconstruction to what we measure. We add some sort of a penalty on types of images that we want to, the total variation of the image that we want to reconstruct, which says that it should be smoothly varying, plus insert something there. So what we're inserting there, for example, for sparse MRI, we're adding the L1 penalty of the wavelet coefficients of x, and so it's a convex thing. For dictionary learning, we just add the dictionary learning penalty of x. So we extract patches from x and do dictionary learning, which is like a denoising penalty. And so you can use KSVD there, and that's been done. This beta process model, which is what I've done with my collaborators. And one nice aspect of doing this is that we can, in this case, don't have to worry about what lambda is, because the dictionary learning does a simultaneous denoising and reconstruction. So, for example, we can set lambda to be something huge, and then learn a reconstruction x with all the noise in it, but then the dictionary learning is going to give us the denoised version along with that as an output. So here's what we get with something like that. So here's toy data. This is 30% Cartesian sampling of this image. And you can see that if we just do zero filling and reconstruct it, we get a noisy reconstruction with some artifacts because of the zero filling. If we look at what we reconstruct by setting lambda to be something huge and then use the beta process as part of the, you could use KSVD here too, as part of the reconstruction. The actual reconstruction is the noisy image with all the artifacts gone from zero filling. So it's like saying, give me, as good of a reconstruction as you can, except for whatever noise is actually in there, not noise because of zero filling. But then so these two images are both, this is not post-processing, these are both output by the same exact one algorithm. So then if you just look at what is it that, using my dictionary and my sparse representation of that dictionary, so if I look at the sparse coding of this signal using dictionary learning and reconstruct that, I get something that looks very nice like this. And so that's in contrast. So I just showed the simplest one if there was no third thing and it was just total variation. But also if you added the wavelet coefficient penalty, I mean, then there's one thing that you're reconstructing, x. And so this lambda has to be traded off to get rid of the noise and do a nice reconstruction. And so this is the best you can do with total variation. Wavelets might not be much better because you have to tweak lambda and all these regularization parameters. So that's a nice thing about using dictionary learning. And I don't even know if I'll be able to get to the point of the talk. So here's quantitative results. OK, so now we want to do scalable dictionary learning. How much more time do I have? OK. So our goal now in a Bayesian view of this problem is to maximize this marginal likelihood on the data. So that's the fixed thing, the sparse coding matrix. These are just the binary encoding matrix and the dictionary. That's what we want to do in this problem. And since I won't get probably through all of it, this is in a very short, easy to read, hopefully, USIPCO invited session paper on Bayesian nonparametric for signal processing. So we can do this with EM, where we treat the weights on the sparse coding and the probabilities of the dictionary elements as being the hidden marginalized variables. And so the outputs of this EM approach will be point estimates of the dictionary and the sparse coding, so 0, 1s and the actual dictionary, and conditional posteriors of the weights on those non-zero, on those used dictionary elements and the probabilities of their use. And so here's the EM master equation. This is what we want to maximize. This makes it easier. We add these Q distributions on the things that we want to integrate out. But there's some immediate issues. First, the variables CI are required. So why do we need to do EM? Because if we want to update the dictionary, we need these weights on the non-zero dictionary elements. So those are needed to learn W in a quick closed form way. But when we want to do the sparse coding of Z, to learn Z, CI gets in the way. Because the update to CI is using the previous values of Z. So if you initialize to all zeros, the CI is going to be a Gaussian with zero mean. And if you looked at the underlying equations, that's saying that there's no dictionary element you can turn on. Because if you turned it on, I think its weight's going to be 0, right? Something like that. So it gets in the way. So what we wanted to do was look more closely at it. And so if we expand the EM master equation, the nice thing is that the conditional posterior of our weights in our dictionaries are conditionally independent, given the sparse coding and the dictionary itself. And so that's why this is not variational inference. You want to set Q to be the true posterior of whatever you're trying to integrate out. And because what we're trying to integrate out is we can actually calculate its conditional posterior given the sparse coding in the dictionary. We can get it in closed form. We can actually set Q. We don't have to approximate it with factorizations and all that stuff that you do with variational inference. So this is the EM in more detail. And in reality, there are many ways that we could factorize things in this right-hand side. And so what we do is instead of, say, picking the full vector CI, we pick only a subset of it and integrate the other subset. So what CIs do we want to focus on? We'll focus on, when we're doing sparse coding of ZI, we're going to focus on the dimensions for CI that are currently turned on, and then integrate out all the rest. So that amounts to the observation that we can write this log marginal of some thing as either this or this. We can keep adding more and more hidden variables. And so think of A as being like one dimension of a CI. And then I'm going to, OK, I turned on a different dictionary element. So now I'm going to update the CI, the dimension of CI corresponding to that dimension. And so this strategy of doing EM, which is a lot like if you know Zubin Garmani and Jeff Hinton's paper 20 years ago about EM for mixtures of factor analyzers, they use the same type of a trick where they don't just write out one EM equation and then solve that. They use this EM equation when it suits them to update this variable, and then that EM equation when it suits them to update that variable. We're doing the same thing. And so here is, I didn't write out the actual algorithm, but here's what you end up getting when you do something like this. When you want to do sparse coding, you again get an activation score of how good is it to add a dictionary element to represent a particular signal, given all the other dictionary elements that have been added. That score has now 3 things. With OMP, it's just a measure of how correlated it is with the residual. Now, in addition to that, we have a prior beta process penalty that penalizes that dictionary element based on how prevalent it is. So if it's not a dictionary element that's used a lot, you're going to have a prior penalty for adding it. And then some additional things that are kind of things that come along with the fact that we're doing EM and have a Bayesian, a probabilistic interpretation. And so we get a thing where we add new dictionary elements, then given the current dictionary elements, instead of doing least squares, we update the conditional posterior distribution on the weights. So least squares, you just find the best weights themselves. With EM, we're doing the conditional posterior on those weights, construct a new EM objective, and then decide what's the next best thing to add. The nice thing with this is that, unlike OMP, where you can always add and get a better and better approximation, so you have to have some stopping criterion, here there is none, because at some point you'll get all negative scores, which says that if I add this dictionary element, I will actually decrease my marginal likelihood, because the goal is to increase the marginal likelihood, and the prior is what makes this possible. So here you just keep adding until you actually adding another one hurts you in the whole scheme of things. Maybe it doesn't hurt you representing the signal, but in the whole model it hurts you according to the marginal likelihood. Time's up. Okay, and so we also made this scalable. Obviously, that part of the title was less relevant to this talk, and showed some results. I'm sorry. So I'll answer questions.
Since we don't have questions, can you give us the kind of short view of this slide? How much of an improvement did these EM approaches make in terms of the scalability?
So for the scalability, the big picture, this is the big picture. Instead of doing sparse coding of every single patch in the image and then updating the dictionary and the weights, all we have to do is randomly subsample some patches from the image. And then instead of globally optimizing the weights, we do a gradient step of the weights. So that's the stochastic optimization story. It turns out that for this specific problem, updating one of the weights corresponds identically to stochastic variational inference, because EM and variational inference are almost identically the same thing, which is nice because that's a big machine learning technique now. Scalability-wise, here you see the red line is using the entire image. We use structural similarity as a performance measure on a denoising problem for this. Blue is if I just subsampled 20,000 patches at random and just focused on that to learn do dictionary learning, and then did denoising based on that. So you can see that it's faster and better. So that's what you would assume. If you have more data, you're going to do a better denoising job. But more data means a slower algorithm in traditional ways of learning the model. Here, when you subsample patches, you also get the better algorithm faster, which is the story of stochastic optimization.
Thank you. Any other questions? Oh, one last one.
So in this, for the purpose of denoising, you're looking at patches, right? So you don't end up, the dictionary elements don't correspond to physiologically interpretable features.
No, here it's little edges and.
There's some way to extend this framework to be able to code images, for the purpose of descriptive, less for denoising and more for
Finding structures and things.
structure.
Yeah, so in that problem, for example, you could do gene analysis. I don't know if that's what you're thinking, but where you have, tons and tons of genes. That's a big data problem, I suppose, but with images, you can easily get millions and millions of patches from a simple image. Even with genes, if you have 10,000 genes, I don't know how much of a gain you guys, but you can you can do that for this too.
All right, well, let's thank John and all of the speakers from the session again.